Okay, response spectra. So it is plot of maximum response. For examples, maximum displacements of a suite of single degree of freedom systems, which give a damping ratio. So the damping ratio is fixed at typically 5%, but it can be something else. But for common design, it's 5%. And with different lateral frequency objects or SDOF systems subject to a specific ground motions loading. So just like this picture here. So imagine this is the base, and on the base we have 5 different single degree of freedom systems on it, and each one has a lateral period. So pretty much like, if you have a simple setup, you have a ward, and then you have a mass on top of it, and you have different length. So when you shake under the same ground motions, or just maybe just a harmonic motions, then you can observe that each systems you have different displacements, or like the shaking reflected on each objects, or each like a mass right there. They will have different displacement response, and that is the response spectra in terms of displacements. So also provided that each of the object here, so each of the SDOF system here, it has the same mass, but just the lateral period, which is the length of each ward over there, is different. So each of it has its own different lateral period, and which can be described by these equations. So it can be used as a filter to see the intensity and frequency content of our ground motions, because again, the response of all this system here highly depends on two things. First, the lateral period of which is the frequency content. So a period and frequency, they are kind of like reciprocal with each other. So the frequency, the lateral frequency of each systems, and also the frequency of the ground motions. So the response of the two combined is the response spectra, which can use as a filter to see the intensity and also the frequency content of the input ground motions. And this is a very useful structural engineering tools here. So kind of like the interface, actually like this response spectra. We talk about this now, and then in module number 2 and number 3, and we always come back to this concept. And perhaps this is the most important concept in earthquake engineering. And this piece of information is kind of like a linked information between geotech earthquakes and also structural earthquake engineers. So experimentally, how do we come up with the displacement response spectrum? Is for examples, we have earthquake acceleration time history, and then if we input it into different SDOF, we have different response. Just like now we have an separated systems, isolated systems. So we input the same ground motions into each of this SDOF systems, and then we record the displacements, the response of each of the systems. And the maximum displacement throughout the input of this earthquake time history give us 1 data point. And we know the natural time period of the systems. So so at a lateral period of the systems of 0.5 seconds, and then the maximum response under this earthquake ground motion is 2.67 inch. So we got our first data point. And at the same damping ratios, now we the lateral period of the system change. Maybe we got like a higher watt right there. So now the lateral period is 1 second, and we got with the input with the same ground motions, we have the 5.97 inch. We got the second data points. So we repeat the same procedure one more time here. So we got another response of response displacements of 7.47 inches, then this is our third data point, so forth and so on. So at different time period, actual time period, then we get different displacement response, and that gives us the displacement response spectrum. So this can be measured experimentally. And numerically, if we want to solve for the response spectrum, then first there will be our geotechnical engineer's responsibility. We have a design ground motions. So again, like for those like displacement response, if we change the earthquake ground motions, we will have different response. And so that's like this piece of information here can be used as a filter to find out the frequency content and also the intensity of the ground motions loading. So if you have this, you can help us to kind of like to find the ground motions we need. So we'll come back to this when we talk about site response analysis. So as a geotech, we design for the ground motions. Very likely for our engineering jobs, we have the design spectrums, and then with that we will select ground motions, and then we can pass the ground motions to our structural engineers peers to do their dynamic analysis, structural dynamic analysis work. And then like we select the electrical vibrations period, and also the damping ratios, very likely for 5%. And we often do work to simplify our system as a single degree of freedom systems. So we can determine the maximum displacement response numerically. For examples, if we know the mass, if we know the stiffness, if we know the electrical time period, then we solve for these equations numerically, then we can find out the displacements, because this equations is in terms of the displacements. And also velocity and accelerations. But if we solve for this numerically, then we can find displacements. So you will be very alike to the procedures that we have used before. So this will be kind of like the governing equations, and this time it will be a little bit more complicated. You will earthquake ground motions instead of harmonic motions right there, and we can solve for a solution something like that. And it will be more complicated than this, because now we have the earthquake ground motions. And we're likely like we need to solve it with some numerical package to save our time. So with one lateral time period and one stiffness, we got one answer. And if we change the mass and also the lateral period, and also the stiffness, then we can have another answer when you subject to the same of the ground motions. Then we will have another maximum displacements that corresponding to the lateral time period. So displacement response spectrums, if we think of some extreme cases, well, first of all, like the lateral time period is proportional to the building height. So if we think of some extreme cases, like where the case that like the height of the building pretty much is 0, if that case pretty much like the system is super stiff, is infinitely stiff. So pretty much like when the ground shake and the building, quote unquote building here is will be synchronized, will be shake with the ground. And the other extreme case is if the building is infinitely long or infinitely tall. So pretty much it will be highly flexible or infinitely flexible. So when the ground shake, our structure or the mass of the structure will ignore, like the rod that supports the mass. Assume this is like a weightless. So the center of mass of this piece over here pretty much will not move at all. But the connections will be keep on waving back and forth. But like the center of mass will not move. So when we have infinity electral period, which means the system is infinitely flexible and the mass will not move. And in real life, like we always have building kind of in between. So we could measure or like experimentally we can measure it, or numerically we can solve for the differential equations. We can calculate how much movement between the buildings and relative to the ground shaking. So a simple examples here. For examples, we have a mass and stiffness and electrical frequency for undamped STOF systems, and this properties to be determined by harmonic excitation tests. So an excitation's frequency of 4 Hz, and the response tends to be without bound, which means that we are at resonant conditions for our tested systems. So we have our first frequency of 4 Hz. Next, the same structure or the same system, we add a weight of 5 pounds to it, and then and then we shake it until it hits the resonance, and we record the frequency this time is 3 Hz. So now ask you to determine the initial mass and stiffness of the systems. So first of all, we know the electro circular frequency, or the which is equals to the square root of stiffness K divided by L, and is equals to 2 pi F. So we can solve for the K, the stiffness, is equals to 2 pi F square 2 times the mass. So we have our first setups, and also we have a second setup, reaching the resonant frequency. So the first setup is 4 Hz with the mass, and the second setup is resonance at 3 Hz by putting an additional 5 pounds to it. And the two systems have the same stiffness. So if we solve for the two equations right there, we got the mass is equal to 6.43 pounds. And if we know the mass now, we plug back to one of these equations, we can find the stiffness of the system is 126 pounds per feet. So we have the displacements, and how about the velocity and accelerations spectrums? And in fact, for our design purpose, we're always interested in accelerations instead of displacements, because we are living in a world that has 1g accelerations, gravities. So you pretty much, in terms of acceleration, is what we want, and also many of our measurements is made by accelerometers put on the field. So that's why accelerations is the way we want to go. So instead of a displacement response spectrums, we 99% in common design, we send out information, so we communicate with the accelerations response spectrums. So this is so changing from domain displacements domains to accelerations domains require an understandings on how to change from frequency from our time to content to frequency content. So if you can if you know the Fourier transfer, it helps a lot. But anyways, the theoretical background, you can go back to your Kramer textbook, appendix A. There are more details about the basic math, how to use FFT, fast Fourier transfer, to change frequency content to time domain. And for examples, when we have a harmonic motions here, so it's a sine functions with an amplitude A, and if we differentiate it, we got the velocity, and if we differentiate it one more times, we got the accelerations with the amplitudes changing. So it change from amplitude A to the electro circular frequency times the amplitudes, and for accelerations it becomes the square of it. 2 times the amplitudes, and that will also create like a phase difference by 90 degree and also 180 degree respect to the displacements domain. So that's why, like, this is frequency. So it will be great like if we can represent our data or our calculations in time domain with frequency domain. So this is the frequency domain. So this is the time domain equations, and this is kind of like the frequency domain formats. So as earthquake engineers, if you want to practice earthquake engineering like professionally, you need to feel comfortable on doing calculations in frequency domain. And if you want to learn more about the background, go back to your textbook, Appendix A. We don't have much time to cover all that. So the amplitude relationships is again like the displacements, the velocity, and accelerations is by the multiplications of the lateral circular frequency. So that's why the lateral frequency is very important. And if you work backward from accelerations to displacements, you will be the divisions of the lateral circular frequency with and without the square, either was of velocity or accelerations. So frequency plays a huge role into amplitudes of dynamic excitations, because this is the frequency. So velocity response spectrums, which can be expressed by these equations. So now we take the maximum point. Pretty much we take the maximum point to be like the velocity spectrums. And velocity can be a mean for us to go to the accelerations. So pseudo accelerations response spectrum, which is the S of A. So this is not like a true acceleration time history, because if this is acceleration time history, then it uses a continuous functions with time. But now pretty much we just take the maximum point. We just take the maximum point on the acceleration time history, which is the greatest points, and we call that to be the S of A. So that's why we call it the pseudo accelerations. And the relationship between the acceleration response will be by the difference of the lateral circular frequency. And the PGA, peak one accelerations, is at the lateral time period equal to 0. And most likely the maximum point is happening at a period that we're very close to the lateral period. So in short, it's like when we have response spectrums in terms of displacements, if we multiply that, we just talk about the amplitude. So this is the pseudo type of calculations. So if we just multiply that with the lateral circular frequency, we got the velocities response. And then if we multiply again with the lateral frequency and then plus the peak one accelerations, that's how we get the accelerations response spectra, which is the one that we most used. And when the lateral period, this is offset by the peak one accelerations. So PGA stands for peak one accelerations. That's another very important parameters. And this one is offset by that, because it's like at the lateral period of 0, if the lateral period T sub n is equal to 0, it's just like what we have mentioned before. We have a super stiff, infinitively stiff systems. Pretty much the mass is shaking with the earth. So that's why when lateral period times equal to 0, that is the peak one accelerations. So that's how we get the accelerations response spectra. And we can use the S of A for the calculations of force on structure. So if we have a simplified structure here, we have the base shear, which is in the opposite directions of the equivalent static force, and pretty much those two are equal to each other, and it's equals to mass times accelerations. And we use the response spectrum, maximum response spectrums for calculations. And the accelerations will cancel out if the gravity will cancel out if you use the S sub A in terms of G's. So pretty much the base shear under earthquake excitations will be equals to a direct multiplier to the rate, because this two cancel out, and then like this will be in terms of like how many G's, maybe like 1.1 G, and then this is your weight. So then like the base shear will be just equals to the weight times 1. And for the moment will be equals to the equivalence of static force, which is equals to the base shear. We calculate times the height of our simplified structure. So a recap on accelerations response spectrums. It can be used to observe key ground motions characteristic, peak ground accelerations, and the SA max. So this is kind of like to the pseudo accelerations that we can use for simple design calculations. And the predominant time period can be baseline. So this is very important. So you know this is your maximum response, and this is your predominance period right there. And pretty much like your design, you want to stay away from this lateral period. So this is your T sub P. So this can be your soil response, or this could be your site response. When you design your building, you don't want the lateral period of the building get close to your response here. Otherwise, when earthquake happens, they will have a resonance effect. And the S sub 8 for soil sites can often be observed at a longer period. And typically, we use 5% for damping to calculate response spectrum. And last but not least, how to design a response spectrum. The International Building Code is 1 year, and also so this the IBC, the Building Code previous simplified versions that as shown here. So some very basic calculations, and I think like your FE exams will touch base on this. Not FE, I'm sorry, the PE exams in California, the seismic one. We'll have a lot of questions covering these topics. And also the attenuations relationships we will talk about in the next module. Those NGA models, next generations attenuations models. And also you can do a fully like dynamic response analysis in finite elements or finite difference. And next topics, we will talk about strong ground motions. I highly encourage you with the reading materials.